Hello, and welcome to Programming Like It's 1979. Lots of people find machine language confusing, and I think that's because the term language is so loaded. In my video, Do Computers Really Think in Zeros and Ones? I propose that the term machine code is actually a better term. Those of you following the NAND to Tetris course through this channel are just about ready to build your own CPU. You've created logic gates, built combinatoric and sequential circuits, and even constructed an ALU, an arithmetic logic unit. But to put those together in a useful way, we need to understand how we're going to communicate our intentions to the CPU through machine code. So in this short video, we're going to hand disassemble a machine code program back into assembly language. Now, just as a reminder, this is a machine and assembly language specific to the hack computer. So the exact techniques I'm using here aren't going to work on your Windows or Mac machine for its native code, but the same basic ideas apply. Let's look at AddHack, our simplest machine program. You can find this file in projects05 of your NAND to Tetris directory. This is going to add two numbers together. To understand it, let's disassemble it by hand into hack assembly code. The most significant bit of each instruction tells us if it's an A instruction or a C instruction. An A instruction just says, put this number in the A register. The first instruction here begins with a 0, which means it's an A instruction, so let's create it now. Our assembly language uses the @ sign as a shorthand for this. @2 means put the number 2 into the A register. Next we have a C instruction. These have more parts. Bits 2 and 3 are unused. Bit 4 indicates whether the ALU will treat the A register as a direct register or as an index into memory. Bits 5 through 10 are used to tell the ALU what computation to do. And these should look familiar to you because these are the same control bits that you implemented in your ALU. Bits 11, 12, and 13 indicate what combinations of the A, M, and D registers the result of the operation is to be stored in. And lastly, bits 14 through 16 tell the CPU under what conditions it should jump, that is, change the program counter to a new destination. So, putting it all together and looking up the values in the tables in Chapter 4, we get D equals A. This instruction just takes the value in the A register and puts it in the D register. To dive a little more deeply here, the 010 is telling the CPU that the D register is the destination, and the 6 aqua bits here, 110000, combined with the 0 blue bit, tell the ALU to emit the A register value. Let's do the same thing for all our other instructions. The third line just stores the value 3 in the A register. The fourth line adds D to A and stores the result in the A register. The fifth line puts 0 in the A register, and the last line of our program puts the contents of the D register into what we call the M register. In this case, that's location 0 in memory. A word about the M register, you can think of it as a virtual register. It's not a literal hard-coded piece of memory that is always the same. Rather, when you refer to M in this assembly language, what the machine is going to do is take the value from the A register, well, let's say it's 62, and it will then find location number 62 in RAM, and it will treat location number 62 as the target of whatever operation you're doing, and we can call that the M register. One final note. For ease of your understanding, the hack file format has the binary numbers represented as strings of ones and zeros. In practice, you'd probably look at code like this on a production computer in a hex editor. In that case, the program would look much more like this more compact representation on the right-hand side of the screen. And that's disassembling a program. So hopefully this gives you some intuition that these ones and zeros aren't just completely arbitrary. They're actually essential, and they're an essential element of how we're going to build our machine. You really do need to understand what these ones and zeros, particularly in the C register, mean in terms of machinery when you build your CPU. And it's a pretty good bet that the way we've segmented these into different kind of zones, that's going to actually translate into a physical layout as you build your CPU. So our next lecture, we will actually dive into what is the task for the CPU. And then there's going to be labs where I'm going to go through and build the CPU with you. I am not sure yet whether I'm going to be able to do that in one video. I like to keep these things to, they've been getting long. I like to keep them to less than an hour, certainly. So I may break that one up into several videos. But I've enjoyed walking through machine language and assembly language with you. I know a lot of people have a lot of questions. There are no stupid questions when it comes to assembly language. I think people are afraid to admit when they find something confusing. This type of thinking, putting yourself in the mode of breaking these instructions down into machine operations, it does not come naturally to anybody. So if you have questions, please put them in the comments of this video, and we'll do our best to answer them. This has been Programming Like It's 1979. Thanks for watching.